Hello boys, as we have seen the last class about neutron diffraction and X-ray diffraction. Today I'm going to tell you about the source of the neutrons and how they are detected and something like why we should use neutron diffraction to identify the diffraction pattern or the shape of the crystals and also the similarities between these two, something like advantages of X-ray diffraction over neutron diffraction and neutron diffraction over the X-ray diffraction. So here in this session, I have not imported any text document. I'm going to write a few important lines. You need to give importance to that and see what can be done. Okay. So for the source of the neutron diffraction, I'm going to write this equation. That is the bombardment of beryllium. That is, you have to write beryllium 94 with an alpha particle Hg42. So it gives rise to 12 6 plus N10 plus some amount of energy that is precisely about 5.7 million electron volts. Okay. Now this the neutron beam obtained from the above reaction is not monoenergetic. So this is the neutron beam and it is not monoenergetic. That is, it means it is having a wide range of energy. So to bring that into the monoenergetic pattern, we have to classify the uh, different types of energy that is faced by the neutron. One is the recoil energy suffered by beryllium, suffered by beryllium, and two is the excitation energy of the C12. So this is 9, and the third one is the kinetic energy of the alpha particle. Okay, as you can see that we have this as the alpha particle, so it has to be with some energy. It is bombarded with that, and then you get a carbon 12 with lot of neutron with some kinetic energy. So these neutrons are slowed down, and we get the optimal, and we call it the thermal neutrons. Optimal means what is required for us that we are going to take up that. Okay, so these three factors decide uh, the energy of these thermal neutrons. There are some other reactions also. I am just going to write some other way in which you can get the neutrons. That is, you put two deuterium atoms, deuterium plus deuterium gives He3, 2. So it's an isotope of helium. So that is why you just write it like this. So you can see 2 plus 2, 2 plus 2 is giving to 4. Here 3 plus 1 is giving you the 4. So that is the balanced thing. And also you can use the Be9 4 and bombard it with the deuterium. So these two are the same. Bombard it with deuterium and you can get boron 10 5 plus N10. So you can see that 10 and 11 are balanced there. And this is the source of neutron diffraction. This is the source of the neutron diffraction. Now coming to the principle why it is being used, as we have already discussed about that. That is the wavelength of the neutrons, right? Wavelength of the neutrons is of the order of the atomic distances. So you should have atomic distance A, B. So there is some distance between them. This distance is of the order of the wavelength of the neutrons. let us see how. This is taken from the fact that lambda equal to h by mv. Because we are taking the wavelength, we have to see this lambda equal to h by mv. Now, your neutrons, I mean, that is the neutrons that are coming out with some kinetic energy have to be bombarded with to the target nucleus. So this have got half mv square is equal to 3 by 2 kt. This is the equation that you need to remember for the population of the neutrons. Population of the neutrons that is governed by Boltzmann distribution. Now, why do we need this? Unless you have certain density of the population of the neutron, you cannot make them available for bombardment. So this is a room temperature population of the neutrons, and therefore you can just calculate V square is equal to 3 by 2 kT by m, and therefore you can get a V is equal to root 3 kT by m. Okay, therefore mv is equal to uh, root 3 kT m. Right? So you substitute this in that first equation. Where is that first equation? Here is this first equation. Simply substitute it is lambda will be equal to h by root 3 kT m. Right? So this is the equation that you are going to get to calculate the wavelength, to find out the wavelength of neutrons. Remember, this is important only because neutron has been considered as particle. Considered as particle. So that is why we are just converting it into some wavelengths with a particular that. Okay. Substituting the values of R, that is K, T and M. So K, I think is the wavelength is about found to be 1.46 into 10 power minus 8 centimeter. You just substitute it, you get lambda equal to this. This is of the order of bond lengths in crystals or in molecules. So 1.46 angstroms, I think 1.46, 1.2 angstrom units is the distance between CC bond lengths. So 1.4 also is there for some multiple bonded compounds, which can put it like this. And therefore this is the order of this is matching with the wavelength. X-ray also have the same wavelength. Therefore X-ray's wavelength and the neutron diffraction wavelength both are used. Both are used as the source of the diffraction patterns. And lastly, in this particular pattern, we are using detectors. How do you use detectors? Detectors is just a reverse of the source. Okay. For example, if you have a fast moving neutron that is coming out, if it is bombarded with this one, bombarded to this particular atom, this one is boron, you will be getting lithium 7 and 3 plus He42. So when you count this, and this is the source. This is used as a detector. Okay. So now the Newton diffraction origin we have studied, and then we are just going to see into the Newton scattering factor. What is the scattering factor? Scattering factor. I think I told you about the scattering factor in my previous class. In this, for example, if you have a neutron, U is having 92 electrons and hydrogen is having 1 electron. So the scattering power of 92 is overwhelming than that of the 1 in the case of the X-ray diffraction. Therefore, hydrogen becomes invisible. So this is very huge. But let me took the values. The neutron scattering factor for is very useful when you have heavy atoms. Neutron scattering is very useful when you have heavy atoms. So let me put the values there. I'll put the values H1, H2, oxygen, uranium. Then on top I write neutron scattering factor, and here you have X-ray scattering factor. Okay, I'll draw a line and then I'll put the values there. It comes to about minus 1.35 for this. This one is 1. This is 2.31, and this one is 1, 2.11. This one is 8, and here you have 3.02, and here you have 92. Okay, you can look at this. If you have a compound like UH3, U and H are involved. These two are involved. And these two, if you look for X-rays, it is 1 and 92. 1 and 92. So 92 scatters more, and it overlaps with the 1 value, H1. So it disappears. It disappears. That is, if you use X-rays, in the presence of X-rays, H cannot be found. H cannot be found. That is what is being said there. H is very difficult to find. But if you use this neutron diffraction, you get the values there. It is 3.02, and this one is minus 1.35. This minus is just a change in phase. So it's nothing to worry. You can just even write it as plus 2. So if I get a peak at 3 points, 1, 2, 3, UH will be getting one peak at 1, like this, for the scattering factor of this neutron diffraction. Okay, but whereas if I use this X-ray scattering factor, I have to count for 92, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, large peak will be there, and then a small peak for hydrogen. So what happens is this peak covers this one. H does not appear. H does not appear. Okay, so that is why this table is very important for you to remember. This table is very important for you to remember because it tells you about the scattering factor of this. So advantage is with X-ray diffraction you cannot find the compounds which are heavier because all are dependent on the valence electrons here. So here you are dependent on the valence electrons. But in the case of neutron diffraction, it does not depend on the valence electrons. So when X-rays are scattered by atoms in phase change of 180 degree occurs, this phase change is given by this value. And under the subheading called as the location of hydrogen is easier with neutron diffraction. It is not easy with the X-ray diffraction. Not easy with X-rays. This is the main difference. Okay. So now we can move on to the next topic in you. What is the next topic there? I think it is something like magnetic scattering, or what is there in your syllabus? I think you have magnetic scattering also. Magnetic scattering. What is a magnetic scattering? Magnetic scattering. You have different types of compounds such as paramagnetic and diamagnetic and ferromagnetic and ferrimagnetic. Apart from this, you have a fifth type also, antiferromagnetic. Antiferromagnetic substance. Now, what is being said here is in ferromagnetic substance, the magnetic property is strongly a highly enhanced, okay, highly enhanced magnetic property. So what happens is, therefore this one is the coherent with the scattering. So here in this case, no diffuse background is present. Diffuse background diffuse means you'll have something which is disappearing. Diffuse is something which is disappearing. Diffuse is just disappearing. Okay. Now in the case of antiferromagnetic substance, there is also coherent spectrum. Therefore, diffuse background is absent. Antiferromagnetic means it's completely no magnetism is there. So no diffuse background. No diffuse background. Diffuse background means I'll show them in the peak like this. For example, if you have something like this, should be some solid peak like this. But if you have some disturbances, this will be followed by a peak like this, followed by something like this. So it's going to give you some disturbance here at this particular place. Okay, so that is why they are calling it as some diffuse background. In antiferromagnetic substance, complete magnetism is absent. In ferromagnetic substance, there is completely coherency. Coherence means agreement. So everything, there is no opposition for the magnetics. So by a study of Newton diffraction, it is possible to distinguish between paramagnetic, diamagnetic, and ferromagnetic by the use of neutron diffraction only. It is possible to study those things. Okay. So for example, in a NiCu alloy, nickel copper alloy, and to say that here you will have some diffuse background with diamagnetic and paramagnetic substances. Okay, in nickel copper, the atoms cannot be differentiated by X-rays. Atoms cannot be differentiated by X-rays. This is because their atomic numbers are very close. For example, copper it is 29, nickel it is 28. So you get peak similar to like this, very close peaks. But in Newton diffraction, uh, the magnetic nickel, okay, so you can use diffraction to identify them. There is some kind of even though neutron is neutral, but it has got a magnetic moment because of its momentum. So this momentum, magnetic moment, because of momentum, is interacting with the magnetic moment of the copper and nickel. So you can see that nickel may be paramagnetic in nature and copper may be diamagnetic in nature. Therefore this magnetic property is answered by neutron diffraction only and not the X-ray diffraction. Neutron diffraction only and not the X-ray diffraction. And likewise, you are going to see something called as the intervalency compounds. What is that? A compound containing element in two different oxidation states. Compound having elements in two different oxidation states is known as the intervalency compound. For example, you take the case of Fe3O4. Fe3O4, it actually exists like FeO and Fe2O3, right? So out of these two, you will have one in Fe2 plus, another one is Fe3 plus. This is ferrous, and this one is ferric. Okay, so that is why you call it as the intervalency compound. Intervalency compound, ferrous and ferric. Now, the two ions differ in their paramagnetic property. These two differ in paramagnetic property. Therefore, neutron diffraction can distinguish between these two. Okay. Fe2 plus, these two ions have different magnetic scattering capacity and therefore they can be very well distinguished. I think I'll just put these things in the notes. It will be very easier for you to understand them. Go through this. If you have any doubt, you can just ask me over there. Thank you for joining me.